Let us solve questions from atoms. So the first question is that choose the correct alternative from the clues given at the end of each statement. Okay, so we'll read the statements and we'll select the correct alternative. The size of the Rutherford atom in Thomson's model is dash the atomic size in the Rutherford's model. So they are asking us to compare Thomson's model size and Rutherford's model size. So it's actually the same. Okay, so the size of the atom discussed by both were same, only the way the charges were distributed is different. Okay, so for this question your answer will be no different from the size in the Rutherford's model. Second one, in a ground state of dash, electrons are in stable equilibrium, while in dash electrons always experience a net force. So for this question, if you recollect the Thomson's model, you will see that the electrons are embedded in a pool of positive charge. So every electron there would experience a net force which is cancelled by the other, and it will be in a stable equilibrium. Whereas in Rutherford's model, the force is not cancelled. So we are experiencing a centripetal force which is provided by the Coulombic force. So always an electron experiences the net force. The net force is not zero in this case. So the answer for this is number 1, that is the Thomson's model for the first one, first blank, and Rutherford's model for the second blank. Yeah. The third question, a classical atom based on dash is doomed to collapse. So a classical atom based on the Rutherford's model is doomed to collapse because in Rutherford's model, as you have studied in the theory, the electron is accelerating and an accelerated charge continuously emits electromagnetic radiation, due to which it should lose its kinetic energy and eventually it should come closer and closer to the positive nucleus, and it should eventually fall on the nucleus, which is the another way of saying that the atom cannot be stable. Okay, so a classical atom based on the Rutherford's model is doomed to collapse. Next, question D. An atom has a nearly continuous mass distribution in dash but has a highly non-uniform mass distribution in dash. So we know very well that continuous mass distribution is in Thomson's model, because the Thomson's model, the electrons are evenly distributed all along the positive charges, and in the Rutherford's model the electron is in orbital motion on the positive charge. So positive charge is at the center and electrons are surrounding it, so which is a non-uniform mass distribution. So I would write number 1 for this Thomson's model, and number 2 blank is for the Rutherford's model. Okay, then number E, the positively charged part of the atom possess most of the mass in Rutherford's model or both of the models. So obviously positive charge is the heaviest part of the atom. Okay, and it is the atom possesses most mass in both the models. So both the models discussed about the positive and negative charges and their masses. So the entire mass of the atom is actually thought of as the mass of proton alone, or the positive charge alone in this case. So both the models will be the answer. Let's move on to the second question. That is, suppose you are given a chance to repeat the alpha particle scattering experiment using a thin sheet of solid hydrogen in the place of gold foil. Hydrogen is solid at temperatures below 14 Kelvin. What results do you expect? So they are saying that if we replace the gold foil by a solid hydrogen, then will the alpha particle scattering experiment can be conducted or not? Okay, so what happens here is the alpha particle, okay, so the alpha particle is very much heavier than hydrogen atom, or hydrogen, generally hydrogen. Okay, so what happens is this alpha particle will not be deflected. It will not be deflected by this hydrogen. Okay, so it will not be deflected, it will just go undeflected through the solid hydrogen. So you cannot perform an alpha particle scattering experiment with a hydrogen atom. That is the answer for this question. Because the alpha particle is heavier than the hydrogen atom, it will not get deflected, it will simply pass through the hydrogen atom. Moving to question number 3. What is the shortest wavelength present in the Paschen series of spectral lines? So we know the spectral lines, the series are actually Lyman, Balmer, Paschen, Brackett and Fund, right? So when we have number 3 in the Paschen series, so when we have Paschen series, that means the electrons can jump, they jump to third orbit. Okay, they jump to third orbit. So the final orbit is the third orbit. Okay, so our equation for finding lambda is mu bar, or that is wave number, is equal to 1 r multiplied by 1 by n1 square minus 1 by n2 square, correct? So here n2 is the orbit from which it is starting and n1 is the orbit to which it is coming and falling or to jumping. Okay, the electron is transferred from n2 orbit to n1 orbit. So in this case n1 should be equal to 3, and for shortest wavelength they are asking shortest wavelength means maximum energy. Shortest wavelength means maximum energy. So in our case maximum energy will be the one which has a maximum difference in energy level. So the maximum difference will be if n2 is from infinity. So from infinity to the third orbit you will have maximum difference or maximum difference in the energy in the case of Paschen series. So n2 is infinity and n1 is 3. So when we substitute, we will get 1 by lambda is equal to r into 1 by 3 square minus 1 by infinity. So 1 by infinity is equal to 0 and 1 by 3 square is 9. So you will be having lambda is equal to 9 by r. And you know the value of the Rydberg constant, that is 1.097 into 10 to the power of 7. So lambda is equal to 8204.1 angstrom. You can calculate it and you will be getting the answer as 8204.1 angstrom. In the fourth question they have given a difference of 2.3 electron volt, that is the difference in energy is equal to 2.3 electron volt, separates two energy levels in an atom. What is the frequency of radiation emitted when the atom makes a transition from the upper level to the lower level? So let us imagine this is the upper level and this is the lower level. So when the electron jumps from upper to lower level, it will emit a radiation, and the difference in the energy of the upper level and energy of the lower level, the difference is given as 2.3 electron volt. So the radiation coming out also must have an energy equal to 2.3 electron volt. That means H nu is equal to delta E, correct? So we have 2.3 electron volt is equal to H into nu. So they are asking us to calculate the frequency. So from this easily we can calculate. Nu is equal to 2.3 into 1.6 into 10 to the power of minus 19, because we want to convert electron volt to joule, and divided by 6.626 into 10 to the power of minus 34 joule second, that is your Planck's constant. So when you do this calculation you will be getting the answer as 5.6 into 10 to the power of 14 hertz. So this will be your frequency. Mu is equal to 10 to the power of 14 hertz. For the next question, 12.5, the ground state energy of hydrogen atom is minus 13.6 electron volt. What are the kinetic and potential energies of the electron in this state? So if you have gone through the chapter, you will know that the total energy is equal to minus of kinetic energy, and the potential energy is equal to minus 2 times of kinetic energy. So you have the equation of the nth energy of the nth orbit. So in that, if you see, you will be getting the values as T total energy equal to minus kinetic energy and potential energy is equal to minus 2 times of kinetic energy. So here they have given total energy. So from this equation, what is kinetic energy equal to? It is minus of minus 13.6, that is equal to plus 13.6 electron volt, plus 13.6 electron volt, and the potential energy is minus 2 times of kinetic energy. So you will be having 2 into minus 13.6, which is equal to minus 27.2 electron volt. Okay, so your kinetic energy should always be positive, remember that, and potential energy can be positive or negative, anything, and total energy also same, it can be positive or negative. So here that is the answer. Moving on to the next question, 12.6. A hydrogen atom initially in the ground level absorbs a photon which excites it to the n equal to 4 level. Determine the wavelength and frequency of the photon. So you are having a photon, a hydrogen atom, it is at n equal to 1, and now it is going to excite by absorbing a photon of energy we don't know, it is h nu, and it is going to jump or excite to n equal to 4 level. So they are asking us to calculate the wavelength and frequency of this photon. So you know very well that the energy of the photon is delta E, h nu. Okay, what is delta E here? E4 minus E1, that is your delta E. It is equal to h into nu. So from this equation, nu is equal to E4 minus E1 divided by h. And what is E4 and E1? So for an hydrogen atom, energy of the nth orbit is minus 13.6 divided by n square electron volt. So we just have to substitute for the fourth energy, fourth orbit, the energy level will be minus 13.6 divided by 4 square, which is equal to minus 0.85 electron volt. And for the first orbit, it is obviously minus 13.6 electron volt. So we just have to substitute in this equation. We will get the frequency. Mu is equal to minus 0.85 minus of minus 13.6 electron volt divided by 6.626 into 10 to the power of minus 34. Since this is an electron volt, we will convert it into joule. So we have to multiply by 1.6 into 10 to the power minus 19. So once you do all these calculations, you are going to get the frequency will be equal to 3.077 into 10 to the power of 15 hertz. Frequency is equal to C by lambda. So therefore, lambda is equal to C by frequency. So we have 3 into 10 to the power of 8 divided by 3.077 into 10 to the power of 15. So your answer for lambda is equal to 975 angstrom. So all this calculation you can do by yourself. So in the next question, 12.7, using the Bohr's model, calculate the speed of electron in a hydrogen atom in the n equal to 1, 2 and 3 levels. Calculate the orbital period in each case of these levels. So they are asking us to calculate V1, V2, V3, T1, T2 and T3, right? So how will we do this? So we have T1 is equal to the distance covered divided by velocity or speed. Yes, so in this case the distance covered is 2 pi r1, because for one single orbit the circumference will be 2 pi r1 and divided by v1. Similarly for T2 and T3, okay, we can write that is equal to 2 pi r2 divided by v2, and T3 is equal to 2 pi r3 divided by v3. Yes, now what is v1, v2 and v3? So v1 is equal to, you know the equation, 2 pi k z e square divided by n into h. So there is another equation for velocity which we can use, okay, that is equal to 1 by 137 into c by n. So where 1 by 137 is called as a fine structure constant. So all that simplification, if you look into the theory, you will know. Okay, so Vn is equal to 1 by 137 into c by n. So we will use this equation because this is much simpler for us to calculate, and we also want to find out the radius because in time period we need r, right? So the radius of the nth orbit is n square h square divided by 4 pi square m k z e square. Yes, so for the hydrogen atom you will substitute z is equal to 1, and if you enter all the constants, you will be getting radius of the nth orbit is equal to 0.53 into n square angstrom. So this is for hydrogen atom, right? Now We will calculate one by one. So V1 is equal to 1 by 137 into 3 into 10 to the power of 8 divided by 1. V2 is equal to 1 by 137 into 3 into 10 to the power of 8 divided by 2, and V3 is equal to 1 by 137 into 3 into 10 power 8 divided by 3. So if you do all these calculations, you will be getting the answers as V1 is 2.186 into 10 power 6 meter per second. Here you have the answer to be 1.093 into 10 power 6 meter per second, and here you have 0.729 into 10 power 6 meter per second. So you can calculate these values and you can verify whether they are correct or not. You can do it by yourself. And the next, what are they asking? They are asking us to calculate the time period. So for time period we also need to know the radius. So 0.53 into 1 square angstrom. R2 is equal to 0.53 into 2 square angstrom, and R3 is equal to 0.53 into 3 square angstrom. So then you substitute in your equation. T1 is equal to 2 into 22 by 7 into 0.53 into 1 square, okay, the whole divided by velocity. So how much velocity did we get? We got 2.186 into 10 to the power of 6. So if you calculate all this, you do the numbers, so you will be getting 1.52 into 10 to the power of minus 16 seconds. Same ways 42, 2 into 22 by 7 into 0.53 into 2 square, okay, this is not 12, this is square, divided by what velocity did we get? V2 as? V2 was 1.093 into 10 to the power of 6. So once you do the calculation, you are going to get 1.22 into 10 power minus 15 seconds. Yes, same ways number 3, 2 into 22 by 7 into 0.53 into 3 square divided by, the answer for this is 0.729, am I correct? Let me check. Yes, into 10 power 6. So that will be 4.10 into 10 to the power of minus 15 seconds. Okay, so these are the answers for T1, T2 and T3. Now there is another short method to do T1, T2, T3. So you know very well Tn is equal to 2 pi into 0.53 into n square angstrom, and here you have divided by velocity. How much velocity did we get? 1 by 137 into c by n. So when this goes to the numerator and you calculate, you will get 2 pi 0.53 divided by 1 by 137 into c into n cube, right? So when we do this, and you have some units here, what is this? This is the time period of the first orbit. So because here n is 1, even here we are multiplying by 1 square. So this number is the time period for the first orbit multiplied by n cube. So I can write the time period of the nth orbit, okay, is 3 n power 3 times the time period of the first orbit. So you can also remember this. So if you calculate T1, easily you can calculate T2 and T3 or T100, whatever they are asking, you can easily calculate this if you know the time period of the first orbit, right? I hope you understood here what calculations we have done. So this is multiplied by c by 1, and this is multiplied by 1 square, this much angstrom. So this and this together will give you the time period of the first orbit multiplied by n cube, because this n will go to the numerator. Yes. So next question is like a subset of the first one. We have already done it. The radius of the innermost electron orbit of hydrogen atom is 5.3 10 power minus 11 meter. What are the radii of n equal to 2 and n equal to 3 orbits? So you know that for hydrogen atom, the radius of the nth orbit is 0.53 into n square electron, and here they have already given like R1 is equal to 5.3, which is the same thing, 5.3 into 10 power minus 11 meter. Okay, now they are asking us to calculate R2 and R3, right? So Rn is equal to n square times R1. So 0.53 angstrom is nothing but R1, right? So you can write n square times R1. So then you will be having what is R2? R2 is equal to 2 square times R1 and R3 is equal to 3 square times R1. That's all. You just have to substitute and calculate. So 4 into 5.3 into 10 power minus 11. So that will be equal to, if you simplify, 2.12 into 10 to the power of minus 10 meter. And R3 similarly you will have 9 into 5.3 into 10 power minus 11, which is equal to 4.77 into 10 to the power minus 10 meter. Okay, so this will be your answer. So look at the next question. A 12.5 electron volt electron beam is used to bombard gaseous hydrogen at room temperature. What series of wavelengths will be emitted? So when the electron beam is having this much energy, okay, all the spectral lines will be seen which can be formed by this particular energy level, photon or electron beam in this case. Okay, so here we have hydrogen atom. So we know that n equal to 1, n equal to 2, n equal to 3 and so on. You have so many energy levels going on, and the energy of the nth orbit is minus 13.6 divided by n square electron volt. So for the first one you have minus 13.6 electron volt, and then it keeps decreasing, so increasing as we move higher energies. Okay, here they have given that the delta E should be equal to 12.5 electron volt. Sorry, that is 12.5 electron volt. Okay, that case you have En minus E1. Okay, so let us see what is the difference is equal to delta E, let us say. So the maximum orbit that is permissible is nth orbit. So we need to calculate the energy of the nth orbit, and hence whatever is below that energy, every spectral series will be visible, right? So energy of the nth orbit is equal to delta E plus E1, right? So what is delta E value? Delta E is equal to 12.5 plus minus 13.6 electron volt. So your answer for this is 1.1 minus 1.1 electron volt. Okay, so that means up to 1.1 electron volt, which energy level corresponds to 1.1 electron volt. So we have the energy, the nth orbit should have an energy of 1.1 electron volt. So in our hydrogen energy levels, we do not have 1.1, we have minus 13.6 electron volt. Second one we have minus 3.4 electron volt. Third one we have minus 1.51 electron volt. Fourth is minus 0.85 electron volt. So you can see 1.1 will lie somewhere here, right? So that means it is higher than the third energy. So from n equal to 3, n equal to 2 and n equal to 1, the electrons can jump, and hence we will get the spectral series from n equal to 3. Okay, so what are the possible series that you will get? So you will get 3 to 2, 3 to 1 and 2 to 1. So these energies of the spectral lines are possible, because 1.1 is lying somewhere in between 3 and 4. So you cannot go to 4, you cannot take the full fourth energy level. So we have to stop at 3. So n equal to 3 it starts. So you can jump to 2, or you can jump to 1, or you can jump from 2 to 1. So these spectral series are possible, and they are asking us to calculate the corresponding wavelengths, right? So the wavelength will be, so you know that for Lyman series n1 is equal to 1 and n2 is equal to 2 in this case. So we will have 1 by lambda is equal to r into 1 by 1 square minus 1 by 2 square, that is equal to r into 1 minus 1 by 4. So 3r by 4. So lambda is equal to 4 by 3r. So first wavelength is this one, that is the Lyman series number 1. Okay, now the second wavelength in the Lyman series will be from n1 equal to 1, but it will jump from third orbit. Okay, so in that case 1 by lambda is equal to r into 1 by 1 square minus 1 by 3 square, which is 1 minus 1 by 9 into r, right? So 9 minus 1 is 8 by 9 times r. So your lambda second wavelength in the Lyman series will be 9 by 8 r. Clear? So you can substitute for the values, we'll do it in the end. And then you have one more line which is coming from 3 to 2. So n1 is equal to 2 and n2 is equal to 3. So this is the Balmer series, first line of the Balmer series. Okay. So in that case you have 1 by lambda is equal to r into 1 by n1 square, that is 2 square, minus 1 by 3 square. So that is r into 1 by 4 minus 1 by 9, which is 1 by lambda is equal to r into 5 by 36. So you have from this the third line will be 36 by 5 r. Okay. So what are the wavelengths that we got? So we got lambda 1 is equal to 4 by 3 r and lambda 2 is equal to, I think it was how much, 9 by 8 r. Lambda 3 is equal to 36 by 5 r. And you know the values of r is equal to 1.097 into 10 to the power of 7 Rydberg constant. Okay, so that is a meter inverse. When you substitute this in lambda, okay, so these are the corresponding spectral lines. So 2 from Lyman and 1 from Balmer series is possible if your incident electron beam is 12.5 electron volt. Clear? The last question in this chapter. In accordance with Bohr's model, find the quantum number that characterizes the Earth's revolution around the Sun in an orbit of radius 1.5 10 power 11 meter with orbital speed this much and mass this much. So they are asking us to calculate what will be the nth orbit if Earth was supposed to be quantized, if the orbit was quantized according to the Bohr's model. So we know very well the Bohr's quantization condition is mvr is equal to nh by 2 pi, correct? So when we have this, we have mass of the Earth and we want to calculate n, isn't it? So we have 2 pi mvr divided by h. So if you substitute, so 2 into 22 by 7 into, what was the mass given as, 6 into 10 to the power 24 into the velocity is 3 into 10 power 4 into the radius is equal to 1.5 10 power 11, 1.5 into 10 to the power of 11 divided by 6.626 into 10 to the power of minus 34. So when you calculate, you are getting n is equal to 2.57 into 10 to the power of 74. Okay, so you can see what a large number you are getting if the Earth's orbit was supposed to be quantized like the Bohr's model.